Hi everyone. So this is one of my absolute favorite reactions in organic chemistry, the Jacobsen Hydrolytic Kinetic Resolution, or HKR. This is a transition metal mediated reaction. In fact, it uses cobalt, and it's a really powerful method in asymmetric catalysis. It has an impressively low catalyst loading. I wanted to give a shout out to this reaction, as it's possibly not as well known as it could be. It really is super easy to do in the lab, works beautifully every time I've tried to do it, and operationally, it's really easy to conduct. Okay, so what does this reaction actually do? Well, it's for making terminal epoxides in really high enantiomeric excess, just abbreviating to EE there. I should note right at the start that this method is probably most useful to you at the start of a synthesis. You probably don't want to be doing it at the end, for reasons that we'll see in this video. Okay, so the general idea is that we want one enantiomer of an epoxide for some reason in our synthesis, as in we want the configuration of that stereocentre perfect. What we do is we do a disconnection back to the racemic epoxide. So that's a 50-50 mixture for two enantiomers, the two different configurations at that oxygen-bearing stereocentre. Now, this is good because it's easy to make epoxides that have a mixture of that stereocentre. For example, some classic ways would be to go back to the alkene. To go backwards, we could use something like MCPBA, or maybe we could use a halohydrin, or alternatively, we could make these from the aldehyde. And that's because I can react this aldehyde with trimethyl sulfonium iodide, that's this salt here, and sodium hydride to go via a sulfur ylide. Those reagents are surprisingly easy to use in the lab, including that salt, which is just a white powder, and you can scoop it out on the bench. Now, this reaction is called a Corey-Tchaikovsky reaction. I'll just pop the mechanism here in case it's unfamiliar. It's actually quite a useful one to have up your sleeve, really, in synthesis. The idea is that this trimethyl sulfonium has an acidic proton that can be quite easily removed by sodium hydride as a base to give me this species. This is just the resonance structure of when you have the sulfene-like double bond in there. But essentially, this is a sulfur-based ylide. We might be more familiar with phosphorus-based ylides, so we might have an idea of what this does with the aldehyde. But there's an important difference. We can draw a mechanism like this, where the ylide attacks as a nucleophile to the carbonyl, but unlike with, say, a Wittig reaction, we don't observe a cyclic product from this. What we get is this intermediate with an O- right next to a really good leaving group being dimethyl sulfide. Okay, it's a bit smelly, but you can remove it quite easily. And then we just get the epoxide. Note that the oxygen-based stereocentre, just noted there with green stars, will be 50-50 R and S configured, provided that the R group doesn't give you any diastereoselectivity. So for example, the Falcon R model isn't relevant, or any other model you might think of. So this is just it, straight attacking 50-50 from the front or the back of the carbonyl. Okay, now back to the Jacobsen HKR. I want to explain how a hydrolytic kinetic resolution works in a general case, and then we'll see how it works in a specific case with the cobalt catalyst that Jacobson and his lab developed. Okay then, so when we've got our racemic epoxide like this, we know that's equivalent to a 50-50 mixture for two enantiomers, so that's just these two structures. And the idea is that we treat the mixture with a single enantiomer of a chiral Lewis acid. Now I'm just going to abbreviate that to La with a little star. So the plan is that one of the enantiomers, say this top one with the up oxygen, doesn't bind anywhere near as well with the catalyst as the other enantiomer. Think about when you shake hands. Your right hand might shake hands much more easily with someone else's right hand than it does with someone else's left hand. And as a result, one of the enantiomers is activated towards being attacked by a nucleophile. So the idea is that this nucleophilic attack happens way faster than attack of a nucleophile on the other enantiomer. So what will be left behind would be the top enantiomer that doesn't bind very well of the epoxide, and also the epoxide open product like this. But importantly, because the catalyst is selectively picking one enantiomer over the other, both of these compounds will just be one enantiomer in the ideal world. Now, in getting this high enantioselectivity, there is a compromise to be made. Of course, if we're only using half of the mixture to form these products, we'll get both of them in 50% yield as an absolute maximum. So this is why this reaction is a resolution. We're using a reaction here to separate the two enantiomers based on the fact that one of them kinetically reacts much faster than the other one. So all we need to do at the end is just to physically separate these. This will often be very easy just using flash column chromatography. Note that there would usually be quite a difference in polarity between these two because one of them has a hydroxyl group and the other doesn't. And so we can use this to form two different things. You know, we might only want one of them, but you can always store the other one and recycle it somehow. Although we've said we only really want the epoxide at the top, it might well be that you really want the other product. So you can use this reaction in either way. It's pretty versatile. So the key idea of this reaction is in this step, one complex forms much more easily than the other. Now in the idealized setup, we're saying that the catalyst is 100% selective at its binding of one enantiomer. Now, of course, the world isn't perfect. If the Lewis acid is not perfect at binding selectively, we should just have a look at what the consequences are. I still start off with my 50-50 mixture of epoxides here. I treat them with my Lewis acid and my nucleophile again. But this time I'm just going to say that the catalyst isn't as good and it is just 90% selective for the intended enantiomer of epoxide. Okay, so that would mean that 90% of the time we'd open the epoxide that we want, and 10% of the time we'd open the one that we don't. So the consequence is that we could get any of these four products. It's the unopened epoxide that we want, but also the untouched epoxide that we don't want, and also the opened epoxide with the stereochemistry that we don't want, and of course the one that we do want. So this is the epoxide that I'm aiming for with the red star. The absolute maximum yield would be 45%, and that will be at the expense of forming 5% of the ring open form here. Same goes, but in reverse for the other enantiomer, we get 45% of this open form with the down hydroxyl, and 5% yield of the epoxide with the oxygen down. So when we look at a summary of this for our products, we still have the epoxide, and we still have this alcohol come from epoxide opening. Overall, we get 50% yield of that one and 50% yield of the other one, but we've actually lost enantiomeric excess here. So we can see if we group these, that's 50% yield total of the epoxide, 50% yield of the hydroxyl group, but within those two groups, we've got a 9-to-1 mixture of configurations. So I can just do a quick calculation for the EE. The EE for both of these products will just be 45 minus 5. That's the difference between the intended configuration and the non-intended configuration, divided by the total, which is 50. And with a bit of quick maths, we can see that that means that these products are forming an 80% EE. So we've taken a massive hit on the enantioselectivity here. The take-home message here is that the Lewis acid catalyst needs to be very heavily optimized, and it must bind very selectively. Just a note here that the enantiomers, of course, can't be separated by normal column chromatography, so all of a sudden this reaction would be much more work. Okay, let's move on to a new slide here. It's about time we had a look at the actual catalyst structure that was developed by Jacobson and his lab for doing these types of kinetic resolutions with incredibly high enantioselectivity. Now, the active catalyst structure is based on cobalt-3, so the +3 oxidation state, and acetylene is a tetradentate ligand that looks a bit like this. Now, the structure of this catalyst allows it to support the higher oxidation state of cobalt, but we can also make this ligand chiral if we pick the correct stereochemistry at these sites here on this cyclohexane ring. Now, I'm going to draw one of the chiral catalysts, where one of the hydrogens is down, one of them is up. You can check for yourself, but this is giving them both the S stereochemistry. Just having a look at the features of the rest of this structure, we have a vacant coordination site there, and that's good because we want to use this catalyst as a Lewis acid. The acetate down the bottom, well, that's essentially a leaving group, or ligand if we're pretending to be inorganic chemists. So we actually start to see some of the symmetry elements here that make this a good asymmetric catalyst. The whole structure will be C2 symmetric if that acetate falls off. Now, around the cobalt, it's going to be an octahedral geometry, and we can see all of this aromatic system as well. So a huge chunk of this is going to be flat, and that's going to be quite important for us when we bind to the epoxides in the HKR reaction. The other key features that will be important are where is the steric bulk, and I'm just going to highlight that in red. The T-butyl groups down the front, of course, project into 3D space and make quite a big steric impact in those positions there. And just having a look at the cyclohexane ring itself, well, actually, maybe I can just draw it slightly differently. On the left-hand side, the cyclohexane ring, the CH2, kinks upwards, whereas the CH2 on the right-hand side kinks downwards. So actually over here, there's quite a steric block, which is also important for determining stereochemistry in the HKR reaction. I just took out my stereochemistry labels there. I'm just going to add them at the bottom again. So this is the SS active catalyst, which has cobalt in the +3 oxidation state. So what I'm going to do is just draw a little cartoon to help me think about this. We've got an octahedral cobalt in the middle of a plane, the binding site at the top, and the leaving group at the bottom. In the corners of the plane, where I'm just putting these red blobs, are where there are bad sterics. But in this corner with the green circle, there's some empty space. Now, lots of research has been done on this reaction, and it's shown that the reaction is quite unusual in that it doesn't just involve the binding of one of these catalysts, it actually uses two. So let's look at an actual reaction that you could do in a lab and how you might deal with this. We start with our racemic epoxide. And actually, the cobalt-3 oxidation state is not something we probably want to be storing. Cobalt-2 would be a much more stable thing to use. So in practice, what you tend to use is, for example, the SS cobalt-salin precursor catalyst. Now, this is just cobalt in the +2 oxidation state. The only other difference being that it doesn't have the acetate group on there anymore. The salin being a doubly charged ligand means that this is all neutral and stable, and you can just store it in the fridge. So what we do is we tinker with our conditions. It turns out the loading of this pre-catalyst is incredibly low. You can get away with something like 0.5 mol%, no problems. Now we need to get the active catalyst for the kinetic resolution. So we need to oxidize it up. And actually all you can do here is just leave it out into the air. It's actually quite an unusual metal type reaction in the lab. You actively have to make sure it's got access to air to make this work. So to get the redox chemistry to work, we need to add a bit of acetic acid. We can just use 1 mol%. That's plenty in this context. I guess we could put air on the reagents as well. And then once we've got our active catalyst formed in solution, we need to add our nucleophile. So I'm just going to do this with water. So if you think back to what we did before, we only need half an equivalent of this because there's only one of the epoxides that should be opening. The reaction is normally done in THF. It's a great solvent for this type of mixture and also for most substrates. Now this will lead to our products. And with this particular catalyst structure, we'll end up with this epoxide with the down configuration, and we'll get the alcohol, well, in this case, the diol, because water was used as a nucleophile. So that's the epoxide opening at the end. And just to summarize what we said before, if we use half an equivalent, we'll get a 50% yield in high EE for both of these structures. Now, research has shown that in this case, it's not just the one enantiomer of an epoxide that binds to the cobalt-3 active catalyst, it's also the water nucleophile. So they both bind to the active catalyst, each to a different one. So what I mean for a successful reaction is that the cobalt has to bind both the epoxide and activate it as a Lewis acid, but also some other cobalt-3 has to bind the water as a nucleophile, and it will actually make it a better nucleophile. If we bind water, one of its protons will become really acidic. So actually that becomes a better nucleophile as well. So kinetic studies have shown that we have to activate both the electrophile and the nucleophile. And this is thought to explain why you get very high enantioselectivity in this reaction. This is unusual in catalysis because there's only a catalytic amount of the catalyst in there. So there'll only be a catalytic amount of each of these structures, and then those tiny catalytic amounts have to meet. Just some basic chemistry will tell you that the likelihood of collision between those two is really low. But in this particular reaction, when they do meet, they're perfectly paired up for a reaction, which actually goes very fast. And only that specific collision can make any reaction work. Okay then, so with that all established, we should try and draw some of this in 3D. First, we should have a look at how the cobalt catalyst binds to the electrophile, so the epoxide. That's the one that's going to open. We've got that vacant coordination site, and I'm just going to draw the binding there in purple. We'll activate the epoxide using one of its lone pairs, and then we need to have a think about where the rest of it orientates itself. We've already said there's quite a bad steric clash by this CH2 at the back. These T-butyl groups in the front quadrants are also going to cause some steric problems. And the more available pocket is kind of here where I've highlighted in green. So we kind of want to orientate the epoxide into that back right corner, maybe something like this. That oxygen center is of course tetrahedral. I could just draw in the remaining lone pair there, and it's been activated by this coordination to the copper 3 center. Now that leaves us 4 positions on the epoxide for the other substitution, 2 going down towards the catalyst and 2 kind of going up. Now, because this epoxide has that strong cobalt-oxygen bond, it's held quite tightly to the salin thing. We really don't want to jam the R group towards it, so we prefer these 2 positions to be hydrogens. And that leaves us 2 other positions. We have to work out which one of these is going to be the hydrogen and which one's going to be the R group. And currently they're out into empty space. And this explains why this reaction must be using a second cobalt complex. We need to differentiate those somehow, and the salin ligand on the bound hydroxide nucleophile can do that for us. I'll also point out at this point that this is why this reaction works so well with terminal epoxides and not so much with any other type of substituted epoxide. The terminal epoxide will have 3 hydrogens in it, so there'll be no competitive steric interactions that might override this binding somehow. Okay, so here's my attempt at trying to draw the bimetallic transition state. It's a really fiddly thing to draw. Apologies, this is the best I can do. We're trying to differentiate between these 2 positions for where we put the R group. What we have at the top is the bound nucleophile. This is the hydroxide bound to the cobalt-3. And below, we have the bound electrophile. So that's the cobalt-free stuck to the epoxide. Now you can see that the preferred assembly of these structures has the top silane rotated 180 degrees with respect to the bottom structure. This will maximize all the intermolecular forces involved and minimize steric clashes. Like for example, all the T-butyl groups are kept a long way away. These T-butyl groups that I'm just circling on the nucleophile are, for example, if we think about the 3D, much further back into the plane than the ones I'm just underlining here on the electrophile. We need to look for steric interactions on the bottom face of the bound nucleophile. Now, the usual ones are the T-butyl groups at the back, just circling them in red. They're going to block the back left and the back right pocket. And the remaining steric block is the CH2 at the front. And now we just need to see where it's best to put the R group. So this position at the back is actually jammed backwards towards these T-butyl groups. So there's a big steric problem there. That's not a very favorable place to put a big group. Much easier to use this front position, which is kind of aligned with the front bit of the catalyst in the emptier pocket by that cyclohexane. Therefore, the lower energy transition state for ring opening will have the hydrogen at the back and the R group assembled at the front. And at this point, we can just draw the mechanism in. That'll be the hydroxide coming down and attacking the epoxide at the less hindered position. So that's away from the R group to ring open the epoxide. So this is the lowest energy transition state for this reaction. Now we've got to keep an eye on the stereochemistry. I just draw your attention to that bit I've highlighted in yellow there. And a quick reminder that this is the SS catalyst. We can see that the structure that binds well into this catalyst and so will be hydrolyzed and ring opened is this epoxide as drawn with the oxygen up. So this enantiomer of the epoxide will open to the diol, so it's the SS catalyst. But the other enantiomer of the epoxide, that's this one here, with the R and the hydrogen swapped in the transition state from front to back, won't bind so well to the Lewis acid because the R group will be clashing with the T-butyls at the back instead, and so will remain unopened at the end of this reaction. Right then, everyone, if you're still with me at this part of the video, I figure you might be interested in doing a deep dive into the practicalities of doing this reaction in the lab. So I'm just going to use one more slide, as there are a few things to think about and address a few questions that you might be having at this point. This is just a picture that I had earlier. I'll just strip away some of the notes. We were very much thinking in an idealized way here, whereas in practice, we probably only want one of these products. So actually, there's a cunning trick that we can play to make sure we definitely get the one we want in really high EE, and that's by slightly tweaking these conditions. So first, what I'm going to do is see what the consequences are if I change my number of equivalents of water. If I put a little bit more water in than I actually need, so I'm going to use 55 mol% or 0.55 equivalents. If the binding isn't perfectly selective, we said before that we might get a lower EE than we intend. Whereas if we add some more of the nucleophile, we can destroy the enantiomer of the epoxide that we don't want by letting the reaction go further. So by having an extra 5 mol% of water in there, what we're doing is sacrificing some of our potential yield to give us 45%, but we're also more likely to have destroyed all of the opposite enantiomer of epoxide that would otherwise be hard to separate. So we'll probably get a higher EE than if we just used half an equivalent. So again, it's this playoff between yield and enantioselectivity. Just following through, that means that we can get up to 55% yield maximum of the diol, but at a lower EE. We will have opened up a little bit more of both enantiomers of the epoxides. So this is actually a really cool trick. If we sacrifice a little bit of yield on a simple starting material to get higher EE, it's more likely to be a more valuable thing for us to use. We can also do this trick, of course, the other way. If I only put 0.45 equivalents of water in there as the nucleophile, the reverse scenario will happen, is that we can get a maximum of 55% yield of the epoxide. That's because not all of it is opening, and this will be at lower EE, up to 45% yield maximum of the diol, but the payoff is to get a higher EE. Okay, and just some other notes about this reaction that might be interesting. Well, quite importantly, both enantiomers of the silane ligand and precursor cobalt-2 based catalyst are both readily available and reasonably cheap. If we have a think about what the structure of those things is, well, they're based on a cyclohexadiamine, and specifically the trans one. And it turns out this is actually really easily accessible. If you do a hydrogenation of this diaminobenzene, you get a racemic mixture of the trans cyclohexane, which is the one we're going to use in the silane catalysts. The cis one is actually meso. You can see it's got a mirror plane in there, but you also form that one. That means that these diastereomers can be physically separated because they are different structures. And for the enantiomers of the trans isomer of the cyclohexane, We can separate by just normal resolution with tartaric acid. Tartaric acid just being in one enantiomeric form. The salts that will form will be diastereomeric, and then they can be separated and free-based later. Okay, next is a point I'd really like to highlight. I think it's really important and often gets forgotten about. This reaction is highly scalable. It works perfectly well at room temperature, open to air, and doesn't require much solvent. In fact, a high concentration is probably helpful, bearing in mind we're trying to get two catalytic species to interact with each other at a reasonable rate. So this very much is a get your precursor out the fridge, put it in a slightly acidic solution, bubble some air actively through it to make your cobalt-3 catalyst. When this is happening, it goes a really deep blood red color, which in itself is always a treat in organic chemistry settings. And then you bung in your substrate and just wait. And if you're careful with your measuring out of equivalents, you should get good results here. And the reaction will stop itself when it runs out of nucleophile, which is acting as the limiting reagent. I probably should have planned this slide out a bit better, but I'm just going to move into this box in the top right. If you go investigating this reaction in the literature, you'll find that similar things also work with chromium. They do a lot of the same chemistry. My understanding is that the cobalt ones are slightly more general, but the general principle behind the whole thing is exactly the same as I described in this video. And the final point I want to make is that you can find this reaction working in the literature with different nucleophiles. I've really focused here on using water and doing hydrolytic kinetic resolutions, where hydrolytic means breaking with water. And among these nucleophiles that you could use to give you some interesting products from this reaction in high enantioselectivity include azides, so that's N3-, bromides, carboxylates, and cyanides. I want to draw particular attention to the azides here because the products of them are so useful in synthesis and chemical biology. The products that you would form would be like this in high enantioselectivity. This, of course, can be quite easily reduced to give these chiral amino alcohols. These play a role in all sorts of bits of synthetic chemistry, including in the synthesis of making chiral ligands for other asymmetric catalysts. I guess the world of chemistry is just all interconnected. If you enjoyed the video, please do give it a like, subscribe to my channel and share it with your friends. Please do let me know your thoughts in the comments below. I've got some other videos on asymmetric catalysis on my channel, and some of them are just linked on the screen now.